Everything you can see right now, everything you've ever seen, every star, every galaxy, every planet, every atom in your body, every photon of light that has ever reached any human eye. All of it makes up less than 5% of the universe. The other 95% is something else, something we cannot see, cannot touch, have never directly detected, and do not understand. And without it, the universe as we know it could not exist. This is not a fringe idea. This is the mainstream scientific consensus, backed by dozens of completely independent lines of evidence from different instruments, different observations, different physics, all pointing at the same conclusion. Most of the universe is made of something. We do not know what. We call it dark matter and dark energy. And this video is about dark matter specifically, the invisible scaffolding on which everything visible in the universe is built. Let us start with the moment the problem became impossible to ignore. Because dark matter was not invented by theorists looking for something to explain. It was forced on astronomers by data they did not expect and could not make sense of any other way. In the 1970s, a radio astronomer named Vera Rubin was studying the rotation of galaxies. Specifically, she was measuring how fast different parts of spiral galaxies rotate around their centers, and this should have been a solved problem. We knew how gravity works. We knew where the mass was. In the stars and gas we could see, and based on that visible mass, we could predict exactly how fast each part of the galaxy should rotate. The prediction was clear. The inner parts of the galaxy, close to the central mass, should rotate fast, and the outer parts, farther from the mass, should rotate slower, just as the outer planets in our solar system orbit more slowly than the inner ones. Mercury is faster than Neptune, and the outer edge of a galaxy should be slow. The data said otherwise. Vera Rubin found that the outer parts of galaxies rotate at essentially the same speed as the inner parts. They do not slow down. As you go farther from the galactic center, the rotation curve, the graph of rotation speed versus distance from center, is flat, not declining, flat. And a flat rotation curve is only possible if there is far more mass out there than we can see. If the mass of a galaxy does not end where the visible stars end, but continues invisibly, far beyond, in a vast diffuse halo surrounding the entire galaxy, a halo of mass that does not emit light, does not reflect light, does not interact with light in any way we can detect, but has gravity. And that gravity is holding the outer stars in their orbits. Without this invisible mass, the outer stars of every spiral galaxy we have ever observed would simply fly off into intergalactic space. The galaxies we see could not hold together. Without something we cannot see, this was Vera Rubin's discovery, and it was initially met with resistance, as all paradigm-shifting discoveries are. But the data was undeniable, and the flat rotation curves have been confirmed for thousands of galaxies. Across every instrument and technique we have applied, the effect is real, consistent, universal, and it requires invisible mass. Now, here is what makes dark matter so compelling as a scientific idea. The rotation curves are just the beginning, because completely independent observations using completely different physics are telling the same story. The second major line of evidence comes from clusters of galaxies, and specifically from one of the most dramatic events we have ever observed in the universe. In 2006, astronomers studying a system called the Bullet Cluster, two galaxy clusters that collided with each other hundreds of millions of years ago, made an observation that is still considered one of the most direct pieces of evidence for dark matter ever obtained. In this collision, the hot gas that makes up most of the normal matter in galaxy clusters, visible in X-ray telescopes as a glowing cloud, was slowed down by the collision. It interacted, it dragged, it piled up in the middle of the collision region, but the gravitational mass of the clusters, mapped using a technique called gravitational lensing, where massive objects bend the light of background galaxies, was not where the gas was. It had passed through the collision, moving forward, unchanged, not slowed down, not interacting, just continuing on its way. As if nothing had happened, the mass and the normal matter had separated, and the only way this is possible is if most of the mass of those clusters is made of something that does not interact through the electromagnetic force, something that passes through other matter without resistance, just gravity, dark matter. The Bullet Cluster is extraordinary because it is not just a statistical inference. It is a direct visual demonstration. Right there in the image, the X-ray gas, the normal matter, is in one place. The gravitational mass, the dark matter, is in another place, separated by the collision. It is about as direct as dark matter evidence gets, short of actually catching a dark matter particle in a detector. And there is a third line of evidence. Perhaps even more fundamental, it comes from the structure of the universe itself. When we look at the cosmic microwave background, the oldest light in the universe from when it was only 3,000 years old. We see tiny temperature fluctuations, ripples in the early plasma of the universe, and those ripples encode the composition of the early universe with extraordinary precision. When cosmologists fit theoretical models to those CMB fluctuations, the models overwhelmingly prefer a universe where most of the matter is dark matter. Cold dark matter specifically, slow-moving, non-interacting with light. This fit is not marginal, it is precise. The CMB data independently require roughly 5 times as much dark matter as ordinary matter, in perfect agreement with the galaxy rotation curves. In perfect agreement with the bullet cluster, 3 completely independent data sets, 3 completely different physical phenomena, all requiring the same ratio of invisible to visible mass, pointing at the same physics. This is why dark matter is taken seriously, not as a theory, but as an observed fact of nature. Something is out there, even if we do not know what. Now, if it is there, what could it be? This is where the story becomes a genuine mystery, because dark matter is defined by what it does not do. It does not emit light, does not absorb light, does not reflect light, does not interact electromagnetically in any detectable way. It has gravity. And that is essentially all we know for certain. The leading candidate for decades was a class of particles called WIMPs, weakly interacting massive particles. The name tells you the theory. Particles with mass that interact only through gravity and the weak nuclear force, not through electromagnetism. They were compelling because the standard model of particle physics already predicted new physics at the energy scales where WIMPs would naturally fit. And because WIMPs produced in the right quantities in the early universe would naturally give you approximately the right density of dark matter today, this coincidence, called the WIMP miracle, made WIMPs the theoretically favored candidate for decades. And we built the most sensitive detectors ever created to find them. Underground laboratories in mines and tunnels, shielded from cosmic rays, cooled to fractions of a degree above absolute zero, filled with tons of liquid xenon or germanium crystals, waiting for a WIMP to scatter off a nucleus and leave a tiny detectable signal. And we have been waiting for 40 years. Nothing. The most sensitive WIMP detectors ever built, Lux, Xenon 1T, Lux Zeppelin, Pandax, have found nothing. Not one confirmed dark matter signal. The parameter space where WIMPs were expected to live has been almost entirely searched and come up empty. The WIMP miracle is looking less miraculous. This does not mean WIMPs are ruled out entirely. They could still exist at masses or interaction strengths outside what has been searched. But the original, most natural parameter space is largely excluded. And this has created a genuine crisis in dark matter physics. If not WIMPs, what? The alternatives are numerous and increasingly strange. Axions, extremely light particles, originally proposed to solve a different problem in particle physics related to the strong nuclear force. But that could also be dark matter if they exist in the right quantities. Axion detection experiments, ADMX and others, are searching for them using resonant microwave cavities, trying to convert axions into detectable photons in a strong magnetic field. Sterile neutrinos, hypothetical heavier cousins of the known neutrinos that interact even less with normal matter. Primordial black holes. Black holes formed in the early universe before any stars existed that could account for some or all of dark matter. The LIGO Gravitational Wave Observatory has constrained some mass ranges for primordial black holes, but certain mass windows remain open. Fuzzy dark matter, an ultralight form of dark matter where quantum mechanical wave effects operate on the scale of entire galaxies, creating a smooth core rather than a dense spike at galactic centers. Each of these candidates has its own experimental program, its own predictions, its own constraints, and none of them has been confirmed. There is also a camp of physicists who argue that dark matter does not exist at all, that instead our theory of gravity is wrong and needs to be modified at galactic scales. The leading version of this idea is called MOND, Modified Newtonian Dynamics, originally proposed by Mordechai Milgram in 1983, and its successor theories. MOND can explain the rotation curve surprisingly well without dark matter, but it struggles badly with the bullet cluster and with the CMB and with the large-scale structure of the universe. Most cosmologists consider MOND incomplete at best, a modification of gravity that works in some regimes but fails in others, rather than a full replacement for dark matter. But the tension has not gone away. And there are newer modified gravity theories, relativistic versions, that handle some of the bullet cluster constraints better. The debate is not fully settled. This is what makes dark matter one of the most interesting frontiers in physics right now. We are not in a situation where we have a theory and are just looking for confirmation. We are in a situation where the evidence for something is overwhelming, but the identity of that something is completely unknown, and where the most natural candidates have not shown up despite our best efforts to find them. The Large Hadron Collider at CERN has been colliding protons at the highest energies ever achieved, looking for WIMP production. Nothing. Direct detection experiments looking for WIMP scattering. Nothing. Indirect detection experiments looking for dark matter annihilation in galactic centers. Ambiguous at best. The absence of a signal after so many sensitive searches is itself information. It is telling us that whatever dark matter is, it is not the simple particle we hoped it would be. One of the most striking things about the dark matter situation is this: we know more about the first second after the Big Bang than we know about what makes up 27% of the current universe. We can trace the expansion history of the cosmos back to a fraction of a second after its beginning. We have a working model of stellar evolution, galaxy formation, the cosmic web that makes accurate predictions across billions of years and billions of light years. And yet, the most common form of matter in the universe, the stuff that forms the scaffolding on which all visible structure is built, is completely unknown to us, not approximately known, not roughly characterized, unknown. It could be a single type of particle, or many types. It could interact in ways we have not imagined. It could be connected to physics entirely outside our current framework. The next generation of experiments is pushing harder than ever. The Vera Rubin Observatory, named after the astronomer who first made the rotation curve problem undeniable, will survey the night sky with unprecedented depth and coverage, mapping weak gravitational lensing across billions of galaxies, giving us the most detailed map of dark matter distribution ever assembled. The Lux Zeppelin detector in South Dakota, the Xenon detector in Italy, are the most sensitive direct detection experiments ever built, pushing deeper into the remaining WIMP parameter space. New action experiments are coming online. New gravitational wave detectors will constrain primordial black holes further, and the theoretical community is expanding its imagination beyond the single particle assumption toward dark sectors, entire hidden economies of particles and forces that interact with each other but barely at all with us. Dark matter that carries its own dark forces, dark atoms, dark chemistry happening invisibly all around us right now. The universe, it turns out, may be a great deal more complicated than we thought. 5% visible, 27% dark matter, 68% dark energy, and even stranger substance pushing the universe apart, the visible universe. The cosmos of stars and galaxies and nebulae and planets and life is a thin, luminous skin on the surface of something vast and unknown and dark, and we are just beginning to find out what it is.